and cheerful welcome to Day 4 of the first Geotech Asia International Conference 2025. It feels almost unbelievable that we have already arrived at the final day of this remarkable gathering. Over the past 3 days, this venue has been more than just a conference hall. It has been a space of ideas, collaboration, and inspiration. We have witnessed knowledge being exchanged, partnerships being built, and visions being shaped for the future of geotechnical engineering. The lively exhibition area, bustling with activity since day one, continues to attract great interest, highlighting the state-of-art technologies, innovative solutions, and the dynamic collaboration between academia and industry that drives the field of geotechnical engineering. Distinguished delegates, I hope you agree with me that from powerful plenary lectures to thought-provoking keynote and invited lectures to vibrant panel discussions and enriching parallel sessions, from the lively exhibition stalls to the warmth of our social anticipation and pride, a grand opening. We open with grace and culture through the beautiful Govind Lam dance, symbolizing light, knowledge, and new beginnings. The inaugural session set the tone with inspiring words from Professor Dasaka S. Murthy, Professor Ashish Juneja, and Dr. Anil Joseph, and the visionary address by Dr. Mark Balaus, President of ISSMG, whose message of geotechnical brothers without borders became the emotional heartbeat of Geotech Asia 2025. The conference was formally inaugurated by the Honorable Minister for Public Works Department, Government of Goa, Sri Digambar Kamath, whose presence added immense grace and significance to the occasion. His words of encouragement to the engineering community of India and his appreciation for the conference's vision to foster global collaboration beautifully marked the beginning of this historic event. The day's plenary lectures were nothing short of brilliant. We listened to Professor Mark Balaus himself share insights on geotechnical philosophies and challenges in laterally loaded piles. Professor Lee Fong Koo discussed deep mixing and jet grounding. Professor T.G. Sitaram captured hearts with his keynote on designing against the odds, the China Bridge, a story of engineering courage. Professor Chung Sik-Yu introduced us to the future of AI-driven smart geotechnology. Professor K. Jian-Shu spoke about advances in trenchless technology, and Professor Katzenberg gave a historical yet futuristic perspective on combined pile raft foundations. The afternoon panel discussion on geo-disaster mitigation in the face of climate change, moderated by Mr. Andrew Namara, brought together stalwarts in the field in an enlightening discussion. It was a perfect close to a memorable first day, a day that reminded us that geotechnical engineering is much about protecting lives as it is about building structures. Day 2 opened with the same enthusiasm. We began the plenary sessions featuring Professor Daniel Antonio Kasufi on geomembranes in embankment dams, Professor G. Madhavi Lada on soil liquefaction and dynamics, Professor Feng Zhang, who introduced his unified constitutive model for geomaterials. The day also brought the enlightening keynote by Professor Kenichi Soga on smart geotechnical infrastructure and distributed sensing technologies, a forward-looking vision of wherever field is heading. Further, technical insights came from Professor Walter on precast slurry walls, Professor Buddhima Ingratna on sustainable waste utilization in ground improvement, Professor Laloy on biocementation and energy geostructures. The day concluded with a lively panel discussion on advances in geotechnical engineering across Asia, moderated by Professor K. Jian-Shu and featuring presidents of Asian geotechnical societies, followed by the Asian Award ceremony and later a wonderful performance enjoyed by everyone, a perfect blend of intellect, recognition and rhythm. Day 3 dawned bright with curiosity and collaboration. The morning began with Professor Nishimura exploring the behavior of unsaturated soils, Professor Robinson discussing consolidation under radial drainage, and Dr. Sam Allen highlighting the role of International Geosynthetic Society in design practice. Professor Anand Kupala followed with a keynote on sustainability and resilient assessments in geosynthetic reinforcement and geothermal technologies, reminding us that sustainability must be central to everything we design. Then came two deeply impactful presentations, the special keynote lecture by Professor Ishikawa of Hokkaido University on storm stability and soil runout integrated analysis, and the keynote lecture by Dr. Mandeep, President of Nepal Geotechnical Society, titled A Decade After 2015 Gorkha Earthquake. Both sessions reminded us that geotechnical engineering is deeply intertwined with safety, community, and human resilience. We then heard Professor Tohata and Professor Hemanta Hazarika, who reflected on lessons learned from the 2024 Noda Peninsula earthquake in Japan, highlighting the crucial role of preparedness and design adaptation in the face of natural calamities. The day culminated in a grand panel discussion, Geotechnical Engineering in a Changing World from an Asian Perspective, moderated by Professor K. Jianshu and featuring the presidents of Asian Geotechnical Societies. It was a fitting finale, a conversation that brought Asia's geotechnical community together to discuss challenges, opportunities, and shared responsibilities. And then came to the gala dinner, a joyous evening of celebration and fellowship. Across all days, the voice of industry added a strong practical dimension through corporate presentations, proving us once again that academia and industry advance best when they advance together. And now, without further ado, let us begin the proceedings for the day 4. May I request our distinguished chair, Engineer Ramesh K. Kulkarni, and our co-chair, Dr. Purnanand Savoykar, to kindly take charge of the first session of the morning. Invite you sirs onto the stage. We have Engineer Ramesh K. Kulkarni as our chair and Engineer Purnanand Savoykar as our co-chair. Welcome you sirs to plenary session 6. To plenary session 9, welcome to all the delegates to plenary session 9, chaired by Engineer Ramesh Kulkarni and co-chair Professor Purnanand Savoykar. Over to the chair and the co-chair for taking up the proceedings. We have 3 invited lectures and a keynote lecture during this plenary session 9. Over to the chair and co-chair.
Good morning everyone. Welcome to this session on day 4. Hope everybody must have enjoyed your stay in Goa and the technical sessions. Many of you must be visiting first time. And being from Goa, I welcome you all for the day 4. So we have these invited lectures today, starting the technical session by Dr. Chaido Yuli Durala Rigby. She is Vice Chair of British Geotechnical Association, and she will be delivering talk on polymer geostructures from the concept to perfection, through lessons learned and good practices. I welcome Madam Dr. Chaido for this section. Madam, you have 20 minutes for this session, and all the question answers you can have at the end.
On. Helps. Good morning. Good morning, Chair. Thank you for the kind introduction. One correction, I'm not a doctor, I'm just Madam. Thank you. So, honored to be here. Thank you for the invite. And apologies I couldn't be here from the beginning. I am actually now the chair of the BGA, so I had to chair my first meeting in London. That's why I'm late, but I only came last night. But thank you very much for the opportunity. So I'm going to take you from the beginning, where we started and where we are today. I'm a geosynthetics ambassador. I work for Tensor, and I have to mention Tensor because Tensor pays my time for being here. So let's go back to the beginning, from the concept of geosynthetics. So everything we do in nature, if you think about it, everything we do in engineering, we mainly follow nature. And there's an example of an aeroplane looking strikingly similar to an eagle, and there's another example of a submarine looking like a whale. And closer to our subject today, which is reinforcing stabilized soil, or soil strengthening, if we look at what the birds do, they stabilize soil with sticks of wood and wheat to make their nests. So the humans have been observing, and we started doing the same. So we take clay, in many parts of the world they still do that, and they reinforce it with hay and sticks to create these bricks that they're called adobe bricks, to build homes. And in many parts of the world this technique is still available. And of course all this concept of reinforced soil started way, way before. And we have many historic examples of natural geoelements reinforcing. So you may have seen these slides before. So this is one of the oldest ones in the ziggurat walls in Mesopotamia, as it used to call there in Iraq these days, where they reinforced low sun with just reeds available in the area. And another example, which is still in existence, is in the Great Wall of China. Some sections of it are also reinforced branches of tamarisk they reinforce the soil. So what changed from the early days to today? So basically we moved from natural geoelements to man-made geoelements, which we call geosynthetics. And today, specifically, I'm going to talk from these types of geosynthetics, which is where it all started. So, I do a lot of STEM talks, and I go to universities and try to encourage students to use geosynthetics. So the first question I ask the students is, who is the father of soil mechanics? Mark's favorite photograph. It's of course Carl Dezaki, so all students know the answer to that. But when I say who is the father of geogrids, there's silence in the room. So my purpose in life, until I retire and leave this industry, is to tell as many people as possible that the man of geogrids is Dr. Brian Mercer. And this is a little bit of an unusual story. Brian Mercer was a very good friend of Salvador Dali, and this is a photograph of the original painting that Salvador Dali did for Brian Mercer, I think 1973. And Brian Mercer was elected as an honorary fellow of the Royal Society in the UK, and this is hanging in the room in Carlton Terrace and in London, and in a room named after Dr. Mercer, in the Mercer Room. And this is a picture of Dr. Mercer with Salvador Dali talking about geogrids. So, 1978, the concept starts, and it's the very first back in the day, it used to be called the polymeric mesh, invented by Dr. Mercer. And it was the first one, is the square one, or biaxial, which now we see everywhere. So this was invented in Blackburn, first time ever, by Brian Mercer, soil stabilization, SS. 1980 carried on, and then the second type of geogrids invented, the uniaxial, so strength in one direction, for soil reinforcement. At this time, it's still called mesh, because nobody else knows what to call it. And then the godfather comes along, Professor Peter Roth of Oxford University, and says, I know what we're going to call them. We're going to call them geogrids. So the name geogrid was given to the industry by Dr. Mercer and Professor Roth from Oxford University, and I hope you didn't know that, so you will take this away with you today. And then the title is The Origin, Evolution to Perfection. So we've done the origin, evolution. So how did the uniaxial geogrids evolve? Well, there's nothing much happened to them. We just changed the length of the aperture to just fit different markets. The applications evolved enormously. So in 1980, the first wall used this uniaxial geogrid was built in Yorkshire, in the northwest of England. That was the very first wall. It was just 2.5 meters high, but it was a railway embankment. So it was a high-risk application, but daring engineers used these products. So fast forward to 2010, and now we're building 60 meters high structures. So this is a highway embankment in the Middle East, connecting Fujairah and Dubai, and the maximum height was 60 meters in three tiers, 20, 20, and 20. And it's so big that you can see it from Google Earth, and that's what you're looking at here. And if we look at the picture of this, is this. So actually there were embankments. So you had the face of 3 tiers and the other face at the back. And the base of the embankment was east, 350 meters long. And sadly I don't have more time to go through this amazing project. So that was the application evolution. How about design evolution? Well, the design evolution developed as well. So in the 1980s, when we built the first structure, there was no British standard. So the first design standard for reinforced soil structures, I believe it started in the UK with the BS 8006, for whoever is familiar. But it was only published, the first one, in 1995, and now we're down to more revisions. And then, of course, other countries adopted or altered the code to fit their market. So we have the Hong Kong GeoGuide 6, we've got the American standards, Australian standards, and also, of course, we've got the Indian standards on reinforced soil. So that's reinforced soil. How about soil stabilization? How did that evolve? Well, that's a different story. So when we first, I was not with Tensor back in the 1980s, I was still at school, but what the engineers did when they, like every engineer, looks for the tensile strength, because that's the natural thing to do. So of course we tested for natural strength, tensile strength, and we put this in the standards. So I believe many DOTs in America, they still use tensile strength. But in parallel, because this is mainly for traffic applications, like roads and working platforms and railways, dynamic cyclic load, we thought, let's go and follow what Astor does and try to do some trafficking as well. But let's try to see how the composite aggregate and geogrid behaves. So since the beginning to now and beyond, because we're still obviously developing and we're still evolving and we're still learning, our geogrids have been tested in many parts of the world. So whatever we say, it's very well documented, and that's how it should be. Innovation and evolution is very welcome, but it needs to be backed by very rigorous scientific justification. And in many parts of the world, so this is the current research that we are undertaking. And the lesson that we learned, it's not a lesson learned, it's like a discovery, is that the soil stabilization mechanism is different to soil reinforcement. And obviously, the inventor of geogrids knew that from the beginning. He knew that he had 2 different products. Because what we found was that the soil reinforcement is tensile strength, whereas the soil stabilization is got to do with the shape, the geometry, and the ability to interlock the aggregate. So as we further, so we are developing and we're evolving. So we realized that the wheel loading, because remember this is mainly for trafficking applications, it follows a 3D radial distribution. So we thought, what if we develop our geogrids to a shape that is closer to a circle, which is the perfect stress distribution? So we came with the hexagonal geogrid in 2007, so we're evolving what our inventor started. But then we carried on observing, because like I said, we keep on learning, we're not there yet. It still surprises what these products do. And of course, we carry on with our R&D, and we saw after 40 years, and we realized that, of course, the particles of the aggregate, they're all different shapes. So we thought, what if we give different shapes in our geogrids? So we evolved in 2021 to the next generation, as we call them, geogrids, that they've got multi-aperture geogrid structure. So by enhancing the geometrical compatibility, we enhance performance. And so the evolution of this type of geogrid is from biaxial to multi-axial to multi-shape, and who knows what's next, because there's always something cooking in the back burner of Tensor's lab. So there is more coming, because we are still in the journey of understanding what our products can do, or our future products will do. And why do we do that? Because the main purpose is to increase aggregate confinement and interlock, because we thought, we realized that this is what matters, ultimately to increase performance and value. And just a very quick example of what value means to us, or what we mean when we say value. Value is, this is a crane mat somewhere in the US. I'm not going to go through the details. All you need to know is the conclusion. At the time was the third biggest rigger crane in the world, I believe. And this is, you can read more for the full story, was the cover page of the March 20, our first e-bulletin of the ISSMGE. So the conclusion is that with geogrids, we replaced 200 piles, 20 meters long piles. So this was a temporary working platform for a crane. And the conventional design was 200 piles to support the crane. So we eliminated all 200 piles just with 5 layers of geogrid and 1.8 mattress. And so what? Well, that's what. And this is what. I mean, carbon is one thing, but money talks, right? Money is the big daddy, like last night. 3.1 million we saved to the contractor. This is done and dusted. That was in 2017. We did it. And there is a paper for whoever is interested. So, to the conclusion, what have we learned towards perfection in practice? So I'm going to give 4 examples about reinforced field compaction, site investigation and foundations, and drainage scar protection. I could talk for hours, but I concentrated in these 4. So, reinforced fill. Our structures are a recipe, just like anything else. Reinforced concrete, if it's C40, you have to give the correct amount and type of Portland cement to reach C40. Our structures are no different. So there's a reinforced soil bridge abutment. It's in integral bridge. Who's Mitchell? Mastermind, my colleague. His design. So 6 meter high, very conventional. We're fighting the industry to adopt reinforced soil because they're so much cheaper, easier, and carbon friendly. So we specified reinforced the fill because it's a bridge abutment, so we need to use the best fill available. Well-graded granular angle of friction of 42. What do you expect to see on site? Something like this, very good quality aggregate. What do we see on site instead? This. So we had to raise our voice, and that was shocking because the specifications were clear. This is a project in Great Britain, and the specifications not only were not followed, were absolutely, what can I say, incredible that this would happen, that they provide this as a granular fill to meet an angle of friction 42. But thankfully we found out, and we raised our voice, big, you can imagine, I don't need to go through the details. So lessons learned, if it doesn't look right, it's probably not right, speak up, because there's always, we're a small manufacturer and provider, and we have to deal with a big contractor. And there's always this disclaimer to say fill by others. it doesn't matter, it's still our design, and we've got the professional duty to warn. Whether it's within our contract or a caveat of exclusion, we raise our voice and we say stop. And thankfully, that's what we did. And yeah, lessons learned, follow the specs. Like I said, it is a recipe. And it was demolished and rebuilt with the proper staff. So I shouldn't complain because Tensa got twice the sale, but that's not my point. My point is that we don't want any of the structures to fail. We want to do the right thing. Compaction. So everybody, of course, knows why compaction is good, but I'm going to give you a different angle. So this is during construction. Accidents happen, and we know that. So this is part of the big walls that I mentioned, and right at the boundary where the new contractor took over, they don't care about our structure, so they're quite rough. So what happens? This big boulder falls down, and imagine we're 40 meters down already. No, we're not. 40, so about 50 meters down. So the impact of this boulder, which is about 4.5 by 3, it's massive. So what did it do? It created a big hole. And I don't know if you can clearly see the geogrids and the soil. So the geogrids are doing their work, and they're doing their work perfectly because the construction in this project was perfect. Because the face of the soil is vertical. But of course we need to fix it because the blocks, the concrete blocks, they're just like to protect long-term erosion. So what did we do? We built the buttress in front of it. So this is the buttress. So we plug. And this is the end of the buttress. And this is the before, after. So it was a very neat solution. So this buttress is 10 meters high. So yes, we can fix it because structurally the wall had nothing, there was nothing wrong with it. And of course we made it look pretty as well. What happens when compaction is not there? So there's another photograph that landed on my desk saying, can we fix it? What do you think? If you look closely, you can see the water from, it's not the water, the sun coming through because there's a massive hole all the way to the top. And clearly, this tells me all the granular materials, the drainage that just poured out, that tells me that there's actually even geogrids must have been missing. Never mind, no compaction. So, compaction does matter. So the answer to that was, no, you have to demolish it and start again. That's the only solution. So all geogrids must be installed and compaction does matter. So, site investigation and foundation. This is another example from somewhere in the world. It doesn't matter. It's a 12-meter high wall. The dimensions are in centimeters. And in this part of the world, the site investigation is done by others and is given to the geogrid designer. So, no control. So slope height 12 meters, phase angle 60, SI undertaking, no boreholes for a 12-meter high structure. Just a few trial pits that they finished at 2 meters. And they found silty clay and no groundwater. Happy days. They gave the bearing capacity, the design, the wall is designed for what it was given. And the only foundation remediation is where the trial pit stops, excavate and replace 2 meters. What have they missed? Well, the obvious, they missed the groundwater level, which was just below, and a very, very weak soil layer with the consistency of plasticine. It was like kaolinite seam or something. So what? Well, take a closer look. So this is the actual embankment, and this was to carry, I think, some electrical equipment. It looks beautiful and perfect, but what's going on there? Take a closer look. But the whole thing is slumping, and you can see the slip circle. I call it textbook failure. So exactly what you expect to happen. Of course, they remediate the foundation, they excavate and replace the 2 meters, but they miss the weakest layer. So that's exactly what happened. So there's the crater at the crest, 3 meters down, and then what happens when it goes down? It comes up. Sorry, there's another one, good scale with the people. The toe comes up, right? The bulging at the top. So the bulging was about 1.5 meters. Like I said, textbook failure. Yes, and of course the water, the culprit of it all. So of course, what happened here, they had to take that away and replace it. Lesson learned? Carry out appropriate SI. So needs to be proportionate to what you're putting on the top to support, not just shallow trial pits for tall structures. and carry out appropriate foundation. It's not one solution fits all. It needs to be bespoke to your structure, to your geology every single time. I think many people say you're going to pay for the site investigation at some point of the project. The best time to pay is at the beginning, because if you pay afterwards, it's going to cost you a lot of money. And sometimes it might cost lives too. So please, don't skip site investigation. So, last
One last comment.
Yes. Last one. So, drainage. Why drainage is important? This is an extra from the British Standard very quickly. It shows that no drainage must die daylight. It must be buried under the soil. So we always put the end of the drainage at the top, buried at least half a meter below the surface. Why? This is a case study from Hong Kong. It's well published. So this is during construction. They stopped for the weekend, typhoon came, but they didn't cover the drainage. So this drainage at the top acted as a funnel. So it took in the whole rainwater in, and because the foundation was concrete, there was not enough drainage for the water to go through. So this is what happened. It popped the face. And in the conclusion in the report, it says the surface water accumulated at the drainage. It was the reason for the failure. So lessons learned, consider drainage at all stages. And scour, and that's the last lesson learned. So in this photograph, what is missing? A lot of scour, as you see, it finishes there. So what? Well, one in a year in the Middle East, there's torrential rain, so these wadis at the base become horrific, like, rivers, and this is what happened. So the scour looks...
Time is done. Quickly conclude in 1 minute, madam.
Okay, and that's it. Then scour, restated, and then followed in different other projects. So takeaways: correct fill type, compaction and all geogrids, appropriate SI, appropriate foundation, and drainage, and provide scour protection. And finally, be open to learning and keep an open mind to foundation, because evolving towards perfection is a lifelong learning journey. And as our civilization, because I'm Greek, so my civilization is as old as your civilization, and that's the last slide. So in Greek we say, I grow old always learning, girasko aidi daskomenos. I cannot read the Indian, but basically your Gandhi said, learn as if you will live forever and live like you will die tomorrow. So in essence, never stop learning, because knowledge has no limit. Dhanyavad.
Thank you very much, madam, for excellent presentation. And you also, madam, we would like to present a memento to you on behalf of this organization. Small memento from here.
Request the chair and co-chair to present a memento to Dr. Chaido Rigby, Vice Chair of British Geotechnical Association, for presenting on the topic Polymer Geogrid Geostructures from Concept to Perfection through Lessons Learned and Good Practice.
There was an excellent presentation of geogrids, and madam also nicely told us how this nature has helped us in developing various geogrids. So next presentation is invited lecture 11 by Dr. Hari Krishna Yendapuri, Regional Manager Director Asia. I welcome Dr. Hari Krishna sir, and he will be presenting on debugging the myth of ground improvement applications. So your time is 20 minutes.
Thank you, Chairman and Co-Chair, for nice introduction. Thank you very much for the entire organizing committee to have this opportunity. It's very good that my earlier speaker touched a couple of lessons learned and openness to have how we can learn continuously. I'm also telling a little bit of a similar theme. There are a lot of myths in the ground improvement area. I thought in this forum with my new role as the Asia Managing Director. We have been present globally over 160 plus years, and in this region of Asia over 5 decades. Singapore and Indonesia, we've been operating for the last 50 years, India for the last 25 years. So I thought to clarify some of these myths, and thanks for providing this great opportunity. So today's presentation is just to have a brief introduction of the ground improvement, what's all about that we look into it, and also the common myths. For some of them, like one size fits for all kind of geotechnical problems. That's not necessarily, and strain compatibility is often ignored, and how important it is to have the strain compatibility in design of the ground improvement techniques. And the consolidation and drainage factor is also one of the very interesting aspect for the full-fledged performance of the intended design. And the ground improvement can be designed as a permanent solution, it's not temporary. And of course, sometimes you have to combine the techniques to suit the varying soil demands and the geotechnical applications. So I thought to cover some of these aspects, but also give real examples to substantiate through case studies. I'm sure you're all aware of this fundamentals of ground improvement. It's all about controlled alteration. It's not a product to make things happen in the ground, but it's all about the controlled alteration. And of course, the response, what we want is out of the engineering actions. It's not the textbook actions, because the ground improvement is more of theory of practice than the textbook formulas. And you can see some of them, like they are all basically connecting to the basics of physics. Sometimes it's a consolidation, sometimes it's a modification chemically, and sometimes as simple as the densification when it comes to vibro compaction, and the reinforcement, very commonly known as vibro replacement or vibro stone columns. And of course, there are other techniques. So in the flow chart, what we believe in Keller is the whole thing is like a life cycle of the project. Right from the design intent, you have to understand the geotechnical complexity involved, geotechnical problems and application that is involved. And when we do into the design phase, you have to take into the account of even availability of materials, constructability, and what is the time that is given, what is the risks that are available in the market. So these are very important aspects of the geotechnical design when it comes to ground improvement. And then additional aspects during verification, like sometimes people don't give importance to the real-time QA/QC aspects. That's very important for the success of the ground improvement project. And then of course the validation point of the right testing, the right instrumentation monitoring, all this gives the right confidence, and you build a track record over the period of time. So some of the myths, I wanted to break those myths and try to attempt in next, in this session, and try to bring those myths connecting to the facts based on the real case studies. So the common myth is like, again, I just wanted to cover all these 5 topics. It's not that one technique fits for all the geotechnical problems. You need to have a right technique. For example, even if you see as simple as the densification technique, right technique in terms of the depth, in terms of the fines content, and the strain compatibility when it comes to the discrete elements. That's very important when it comes to slope stability and liquefaction applications. Drainage, whatever we wanted to achieve through right consolidation, the drainage aspect can never be ignored, and how it can be designed as a permanent solution, not just a temporary, and sometimes the combination of techniques. The first one, touch the first top 2 rows. We do a lot of reclamation projects in Southeast Asia. Projects, we have to ensure the fines content, how clean is the sand, what is the calcareous content sometimes that you have in the reclamation projects. And then you can actually decide on the vibro compaction or dynamic compaction, depending on the depth, depending on the water table. And when you deal with the soft clays also, you have to take into the account of whether sometimes there is any organic content and decayed wood. That is also important when you choose to have reinforcement technique like white rolled stone columns, or sometimes you have to go into deep soil mixing. So I think all I'm saying is diagnose the soil very well ahead of the time and then select the right appropriate ground improvement method to fulfill the right geotechnical application in the performance. Then myth 2 is connecting with the strain compatibility. This is more important when it comes to slope stability application or liquefaction-induced earthquake-induced movements to address the liquefaction mitigation. Because for these lateral movements, it's very important that you cannot have discrete elements taking undue lateral displacement causing the unwanted failures. And sometimes even in the design, let us say slope stability, you forget the natural depression right next to the geometry of the project. And there may be a valley, there may be a lake, there may be a pond. That will cause unwanted excess movements, and then you have to take into consideration the strain compatibility when you look into it. I'm going to substantiate that with this case study. It's called the Pungal Waterway in Singapore. It's been up and running for the last 15 years. It's a natural river. You can see on the left-hand side and right-hand side. These two natural rivers connected with this artificial canal. And the depth goes to about 5 meters of depth. That will be clear in this geometry. You have a top fill followed by very soft clay, and the clay can go as low as 10 kPa of a shear strength. And this very soft clay, when you wanted to place a discrete elements like rigid inclusion or deep soil mixing, you cannot take with one element right strain compatibility. And with this, and how you can have one element connecting to like 10 kPa to 500 kPa, like that's UCS of 1 MPa and CU of 500 kPa, but still not good enough when it comes to strain compatibility. Then you have to take this into the account, into the design phase, how you can actually come up with, now this is the waffle design we call it. Basically, you're connecting some of the columns with the right overlap and making that grids optimized also. For example, below the canal, you can optimize the depth for not having the unwanted cost involved in the project. But where it goes to the slip failure, like if I can take the pointer here, you can see here how critical is to have the slip failure movement, and then that is design is taken, not leaving as a discrete element for not having the strain compatibility. So this way you can ensure the right strain compatibility and design the whole project for the right geotechnical application. And that's the execution phase of deep soil mixing, and that's the phase of under construction of the canal, and that's the phase with completion, and it's up and running for the last 15 years with the right strain compatibility addressed in this case 3. Moving on, next important aspect is the drainage and consolidation application of soft clay behavior. When I was a young engineer in Malaysia, this is way back in 2004, and it's there for the last 20 years. It's a very interesting case study for us. And this is in Kuala Lumpur, and what we have, this soil is called slime. Slime is nothing but very soft, ultra soft silts, having some sand contents inside, but it's very soft. Shear strength sometimes goes as low as 8 kPa, and maybe as high as 20 kPa. And these very soft, you can see how badly even the excavator of 20-ton weight is sinking into the ground. So you cannot take that kind of a weight. Imagine now you are putting huge reinforced soil wall having 13 meters height for this interchange. How this is going to be? So that's, we are talking about 260 kilopascal. So it's just not possible without having the right soil improvement, ground improvement technique. So what we have done is, of course, again, the optimization of the elements like the closer spacing with a higher replacement ratio to address the slope stability, and you can actually optimize at the center of the carriageway of the highway, because that's more for settlement, and being RSO, you can have tolerance of even 300 millimeters of settlement as long as it's constructed rightfully. And then stability is ensured with the right factor of safety of 1.4. But what is more important is the drainage layer. The drainage layer ensures the right consolidation behavior of the soil as it gets filled. And this is a very interesting instrumentation monitoring, ran up to almost for 3 years. What is very important even in construction phase, like 13 meters, we took 13 weeks to build the embankment. That's almost like 1 meter per week. And if you accelerate this, I want to get this done over 1 month period, every week let's build 3-4 meters, that also can cause a lot of problem to the soil. So it has got drainage elements, it has got drainage layer and all nicely connected. But you need to have the right sequencing of construction to ensure that whole performance is achieved in the rightful direction. And you can see the nicely available wall for last maybe 20 years, since 2004, and it's working very well, 13 meters high RE wall. The last two case studies, very quickly wrap it up. I'm looking at the clock, so thank you, Chair, for placing that timer. The myth 4 is also to see how best we can actually design the ground improvement for the long-term applications, just not the temporary. Although the earlier two case studies, you can see 15-20 years, they are also permanent applications. This one, very interesting in Jurong Island rubber factory, where it originally designed to have the driven piles, precast driven piles, and we converted this into vibro compaction technique because we found the sand is good enough having a reclamation, but it's not having the right densification. So we've also monitored out of the client request, this is having about 7 years of monitoring data, and the whole factory was monitored to have just 32 millimeters after the right densification of the loose sandy deposits. And when the factory is intended for a raft of 50 millimeters performance settlement, so we changed from a very expensive piled solution to ground improvement solution. And you can see the Lanxess factory that's there also for last maybe 15 plus years. And I just wanted to show this next picture. This can be done for many other structures. It's very pride because it's my home. I live in one of the dwelling here. This is a residential community in Chennai. It's also, we monitored for last 10 years of settlement as we converted piled solution to ground improvement solution to have this, rightly connecting to the long-term performance of the structure. The last case study I wanted to touch on, sometimes you get into surprises of soil. That's why it's very important. You need to have confirmatory soil investigation for every ground improvement project or every foundation application per se. And this is the one example from the India, from Ayodhya, where we have beautiful temple now already inaugurated. And this is the STP project in Ayodhya city. And you can see the structure of the STP here and some detailing. I'm not going to the details, but main application is the liquefaction mitigation with having 0.24 G with a magnitude of 6.5. And how we actually can, validate the soil confirmation. So the tender stage, it says liquefaction depth is only 10 meters. But when we did the confirmatory soil investigation, liquefaction depth became 17 meters. Then sometimes you are in a stage where design and build, maybe lump sum contract. How do you deal with this? So then one other interesting thing we came, actually, unlike the top 6 meters, 7 meters, having, let's say, higher fines content, having 20%, but the bottom we found actually relatively clean sand. It's a river deposits that's maybe there over the sedimentation process, over the decades of sedimentation. And then we actually wanted to optimize, can we not combine the techniques than just sticking onto the same technique, because you have varied soil profile here, and that's actually going to complement your geotechnical design in a complex way, but also you can optimize the solutioning by combining the two different techniques. So what we thought, vibro compaction at the bottom layers, like bottom 10 meters depth, where you have less fines content that's suitable to have a densification effect to address the liquefaction mitigation, but also to have the vibro stone columns at the top, because fines content is more, and it's not that one solution fits for all the problems. You need to change to vibro stone columns where the fine content is more. Then you can actually cause more reinforcement effect, and causing that drainage is good enough to mitigate the liquefaction mitigation. So we've addressed the deeper problems, what was not detected in the tender stage. We've addressed the varying soil condition by combining two different techniques. Thereby you actually can have proven performance. You can see how the low test results, and these are all the dots of pre treatment and how best, all the less than 10 SPT became now 20 to 30 SPT post-treatment. So you are able to mitigate the liquefaction for this project. So that's the last case study. I'd like to summarize now by having these case studies and then trying to bring some facts to break the myths of some of the misconceptions that we face in day-to-day life. Firstly, GI is just not one size fits for all the geotechnical problems. The complexity, variability of the soil, different performance criteria, different structures do place a different significance of the geotechnical design. So we need to engineer the solution and just not assume one product fits for all the problems. And the second is the focus on addressing this strain compatibility becomes even more critical. If you are transmitting all the loads through deep foundations, maybe the strain compatibility is less important. Although there also you need to have soil, structure, interaction, compatibility. But here, discrete elements, sometimes rigid elements can be rigid inclusions, can be deep soil mixing, especially for the applications like stope stability or liquefaction-induced mitigation problems. Then you need to have the right overlapping techniques, the right grids, and the right understanding of the complex design before it gets execution. Then it is possible to have the different techniques combined to suit the varying soil conditions, and that will actually give leverage on optimizing the cost as well as the time. And more importantly, nowadays you can have a lot of carbon savings because we don't use cement and steel in ground improvement techniques except maybe deep soil mixing, but steel definitely we can optimize to a great extent unless it is really required, like having a reinforcement element in deep soil mixing. But most often, if you compare like apple to apple, you can have huge savings on the carbon footprint for a geotechnical design. The last, which is very important, the QAQCs plays very significant role for successful delivery. And overall, I conclude by saying GI can be cost effective if you design it well, faster compared to conventional solutions, and it's greener by having the right carbon savings. Thank you very much for your time.
Thank you, sir.
Thank you very much, Dr. Hari Krishna, for in-time presentation and very nicely bringing out various myths and the realities in ground improvement as regards strain compatibility, long-term stability and all. On behalf of Geotech Asia, I request my chair, Engineer Ramesh Kulkarni sir, to present the memento to you.
Request the chair and co-chair to present a memento to Dr. Hari Krishna Yandamuri as a token of gratitude from the organizing committee of Geotech Asia 2025.
Outside, yeah.
Next invited lecture 12 is by Dr. Ratnakar Mahajan, Technical Head India, Southeast Asia Pacific region for McAfee, and he'll be delivering a talk on building green infrastructure using geosynthetics. I welcome Dr. Ratnakar Mahajan to the address.
Very good morning to all. Just looking at the date, maybe I am presenting in future, but it's a typo. It's not 20257, but it's 2025. I'm talking of building green infrastructure using geosynthetics. I'm talking about element of one of the important element of 5 elements, that's water, which is, I think, a friend and enemy for geotechnical engineers. Optimum moisture content, we are able to get the soil compacted to the required density. Whereas if you have excess water, then compaction is an issue, poor water pressure is an issue. And I think whenever you have very heavy rainfalls, the geotechnical engineers gets calls very quickly, That's the time, but that's where I'm going to address what does this water means and how we need to manage it in terms of long-term performance of the structures, because if that's not being addressed, there will be a lot of issues. Conventionally, we deal with this problem using the conventional materials, that's typically mined materials, gravel, sand. They are basically sometimes available, sometimes not available. And looking at the current scenario, I don't have to explain. But for example, this year in India, the rain started in May, which were supposed to be started June, and supposed to end by September, mid. But still, I think some parts of the India are receiving rains, and we have seen the worst debris flow events in state of Uttarakhand, Dharali. We have seen the worst debris flow events in northeast part of India. So the conventional solutions, they are efficient, but of course need to be seen from what exactly how they will perform. So I will be talking on the drainage. Of course, we know a set of operations through which we remove the excess water, either through subsurface or soil. And in case it's not being removed, then there are sorts of problems. Not only the geotechnical stability, but also even the safety point of view. So, the famous retaining walls, which all geotechnical engineers knows, the water can create a havoc and you have failures. A canal, of course, very nice structure, but in case you have water table very high level and you have empty canal, then you have issues of linings, and this was the case in state of Punjab and Haryana, because that's the two states, the biggest canal irrigation system is there. And usually we will provide drainage layer at the bottom. Or just what we are talking of ground improvement, you have excess water, poor water pressure, or sometimes we need to build the structure on it. So strengthening plus drainage is both parts being taken care of. Landfills, of course, we are talking of draining of liquids as well as the gases, which is part of your bottom lining system or top lining system. Pavement, the granular surface layers, be it a flexible pavement or a rigid pavement, can have a daylighted granular surface, or you have situations where anticipating a lot of floods and you want to keep your subgrade dry, so you go with conventional open drains, or sometimes you go with the trench drains built with the gravels. In case stagnant water and fluctuation, so capillary rise cannot be avoided, the conventional solution is placement of sands, typically maybe 150 to 300 mm sand layer, which will cut off the capillary rise. Or you have a situation where we are looking at pavement, maybe in a hilly area, again the rising of groundwater is an issue. You have trench drains, typically in cuttings, especially if you see our Himalayas or the Western Ghats, you have some areas you have constant sinking and constant pavement issues because of the phreatic surface being cut. Sometimes we have infrastructure close to irrigation canals, and then there you have these issues. Apart from subsurface, there are surface drainage measures to be taken care using the chute drains, something like this if nicely being done. Even the big structures like dams, may it be the small or big, we look at the chimney drains. And of course these are some pictures from International Geophysical Society where you can have multiple applications of geosynthetics as a part of drainage. Apart from that, tunnels, railways, So I think we are touching all the places. This is a sketch from Indian Railways. This is an old one where 600 mm hand-packed boulders are placed. Hand-packed, not boulders, hand-packed. Now they have changed it to a little bit hand-packed boulders plus a cement layer. This is from Indian Road Congress. Again, it is 600 mm thick, well-graded drainage layer. Now that's being specified. We will dwell on this, what all these mean, hand-packed boulders and well. Obviously, I think we need to go to long back when we talk of drainage. We know the filter layer, how to design based on the base layers or the soil available. Nice designs can be derived based on the D15, D85, okay? And then you have nice curves where you can look at the gradation of the base or core material as well as suitable filter material that we can choose. I am not going to go in the design of this. But my point is, even if you do all these calculations, what it needs is a drainage layer which is having certain gradation to be placed in a certain pattern. Inverted drainage layer, sometimes open drainage layer, depending on the what type of soil you want to retain. And then, of course, you have the curves for textiles where you can look at the opening size and derive it. But how often have you seen installation of a drainage layer, what's being designed with a different gradation? At least, unfortunately, being civil engineer, I need to admit, last 2 decades I have not seen so seriously being done. Some portion it's being done, and some structures I have personally seen how it's being done. Most of the time you will end up something like this, maybe a single size drainage layer being placed with the soil, and what's the life of this drainage layer over a period of time as time passes is to be seen. On top of that, there are issues of banning of mining for sand and gravel. That's specifically in India is happening. Certain parts we have these issues. So when it comes to solution for this, of course, drainage composite is one of the solution where you can look at a product with a textile, a drainage core, and on other side maybe a textile or a membrane. So the functions what it will do as a drainage, apart from that filtration, separation and protection. You can have variety of drainage composite with only one side textile or both side textile or one side geotextile and one other side membrane. The reason I have just put these basics is I have seen in university sometimes people are using only one type of drainage for many applications. This is very interesting picture or let's say drawing from IRCS 59 2002. Of course now IRCS 59 has been revised, and those who are interested can go through the paragraph about how the drainage happens and how the filtration happens. So basically in crux, when you have the aggregates wrapped in a geotextile and then you have soil around it, over a period of time it forms a filter zone. So initially there will be some loss of fines and then slowly the soil itself will be its inverted filter. Subjected to if you have a proper geotextile or a proper conventional drainage being designed. Of course, when we look at the conventional method and the geosynthetic drain, we are looking at the criteria like graded filter. In geotextile, you can actually customize, you can make the textile manufacturing with the choosing the apparent opening size. Whereas we have seen in case of conventional filter, you can do it, but you will need to construct that way. Quality, of course, it depends on the source from where you are mining the minerals or the drainage layer. Geotextiles, of course, are coming as a part of polymeric materials which you can consistently build. And ease of construction is very, very easy to construct. Cost, obviously, from different states of the parts of the India, we have seen it can range 20 to 40% very easily. And carbon footprint, of course, of this solution is very low. This is one case of canal which you can provide a drainage composite at bottom, especially critical when you have water table very high and possibilities of cracking of the canal lining. Or PVDs, it's a replacement of conventional sand layers or gravel layers. Or you can use a geocomposite in the pavement layer, especially for areas even for frost susceptible soils. Of course, here you will need little different drainage composite compared to the other locations. Or you can look at drainage composite for cuttings. So all these sketches what I am showing are a part of the norms and guidelines now in India. Or you have a cut and cover tunnel, you will need to provide a drainage composite on top. Retaining walls, of course, one of the requirement would be to design it now for these applications. When it comes to the application of design, whether it is landfill, you are dealing with leachate, whether it is retaining wall, you are dealing with the natural soil, with water, you are dealing with pavement, the applications are different. So here we will need to first understand what are these boundary conditions and then design. Here, of course, you can choose the drainage composite based on the flow rate, and when we talk of the available flow rate, of course, we will need to see the conditions through which it's going to be subjected to with a design like what you will see. I have just put one simple example of a retaining wall. In case you want to estimate how much flow it will accumulate at the top, you can just go by first principles of equipotential and flow lines and calculate the flow. Drainage composite or geocomposite drain must have a higher capacity than what the flow is expected. Keep in mind the drainage composite, what we are going to put, need to be compared with the conventional, maybe based on the type of gravel you want to put. Take the K value and Q is equal to KIA. From that you can calculate the flow. So for example, if you take a 0.6 meter drainage layer, which is being specified in the various norms, and let's say a vertical wall, so you have gradient of 1, maybe 0.6 liter per meter second, that the flow you are looking at. Now for arriving at the flow capacity, you can choose a drainage composite with a testing as per ASTM or EN ISO. You will get a flow which is determined from the laboratory. You say the QL is the flow from the laboratory, and then you will need to understand the available long-term flow. The long-term flow will depend on the life of the structure. So whether it is 20 years or 50 years. So the question will go, how does it matter of the 20 and 50 years? Because the drainage composite will be subjected to the weave. It will deform, it's a synthetic material. The textiles will deform over the drainage composite layer. So intrusion of geotextile will happen. Then you have clogging. So if you are dealing with the landfill, there are chemical clogging. If it is we are talking of a retaining wall where you are subjected to have a rainfall, not expecting much of the difference in chemical, then it will be biological clogging need to be seen, both chemical and clogging. The important part is to take care of all these factors and then choose geocomposite, not just the value coming from laboratory and compare it to what you get as an input. On top of that, very important factor, FLR is an empirical factor which need to be applied, because in field there are variety of conditions, but it's not possible to test composite for all of this. You may test for one condition and extrapolate to the other condition. For that, the FLR value can be applied. So for example, I have tested a drainage composite with one side a steel plate, other side a rubber, simulating a concrete retaining wall, because concrete is rigid whereas soil is soft, so there will be a geodextile inclusion. But in case if I have to use it for soft condition, you can do that using this FLR factor. So this is what you can follow as per ASTM or about various loading conditions and the gradient you can choose. And of course, very important part, the geotextile will need to be designed. I will leave the copy of presentation. I will not go in details of this, of designing. I would like to point out one aspect. Many a times I get a question, why can't I use a geotextile, very thick geotextile, 500 or 1000 grams per square meter? You will need to understand there is a curves from the Cohen's group, geonet properties and geotextile properties. If you subject it to a certain pressure, let's say a 50 kPa pressure, the performance of the geotextile in plane flow is quite different than the drainage composite core. So that's why the drainage composite is best suited rather than going for a very thicker geotextile. Case study very quickly. This is a case study from the state of Haryana. This is a canal lining which feeds the certain part of the city and the irrigation also. And here the ground water table was very high. Here we have provided solution with a drainage composite. The black color sheet what you see is basically a membrane, and on the side over the contact with the substrate is a geotextile. So this is the initial site condition in 2009. So there were a lot of issues in terms of lining getting cracked, and what photograph you see is basically they have dressed it up first. After removing it, after 4 years of the construction, that was 2013, we took this photograph, and the authorities of Haryana Canal are really satisfied with the performance. This is a case from eastern part or northeastern part of country. Due to some confidentiality, I don't want to disclose the project. But here the soil is very soft, and here the prefabricated vertical drains are installed. And this part of the country, the sand is not really available, gravel is also not available. It is very expensive. So we have used a drainage composite, and you can see the drainage composite itself is now fully saturated, and then we will build the embankment on top of it. This is a very interesting case. Again, due to confidentiality, this is a border road project in the Himalayas for security forces. Very high altitude. So there was a patch of the road which they had treated for almost 2 decades, but every year they had to go and redo it. And the engineer said we need to look at the drainage part of it. Here then we installed the drainage composite, of course taking care of the parameters what I have discussed, and this is a during daytime, temperatures are -10. And this is a summertime what you see. And here of course the installation of the granular surface layers on top of drainage composite was done. After the installation of this, it's almost like 6 years back. We have no news. No news is a good news, right? This is another application of like on highways where you have these issues of high water table. You can go with the trench drains replacing the conventional gravels. This is a project on National Highway NH8, very close to Delhi area. Here the masonry wall behind that gravel was there, which we actually replaced it around 2008. The first photograph what you see is the masonry wall. On the back side they put the drainage composite, and the authorities were saying you are not giving us right product. 600 thick drainage bay cannot be replaced by your 4 to 5 millimeter thick drainage composite. So we did a demonstration. We backfilled the wall and then we placed the tankers on top of it and flooded it. And you see from the V-folds the water came, and that's how they got the idea. This is a project we did for railways. Railways are very particular about the use of such technology. So we did a trial mock-up for the Eastern Dedicated Freight Corridor. For your information, the low LHS, they call it as the low height subway. Here for them it used to take almost a week's time to place each boulder, hand-packed boulders as per the specification, whereas with the help of a crew of 4 people, they could complete installation in 1 day for one LHS. Some photographs I have captured because we did some field trials to show them how it is working. So this is a video from northeast part of the country. Very heavy rainfall, and backside it's shells. And you know shells required drainage, so here drainage composite was provided. The right video is showing basically the behind a retaining wall, a drainage composite was placed of 10-meter high retaining wall, and then it was flooded with tankers to sea. And after their confidence, contractor L&T and the authorities agreed for this kind of solution. For your information, now railway standards in India allow use of drainage composite behind retaining walls. This is information of course related to the drainage composite. If you take behind retaining wall, you are looking at maybe 1 truck of drainage composite, which is equal to 150 trucks of gravels. So it's not only the cost of material, but look at the environmental saving what we are looking at it. Mining is limited as well as
Dr. 1 minute more.
Yeah, sure. Done. Summary. Last. So this is a better material, proven material. Of course, as I said, we need to understand what environment we are working. Number of factors like creep, chemical clogging, biological clogging, intrusion of geodetic sediment to be seen, low carbon footprint, building its the green infrastructure, and here you need to have due diligence. Of course, all this is aligned to the Sustainable Development Goals. We are looking at 8, 9, 11, 12 and 13, looking at material savings, outstanding performance and faster installation. My message is I think it's time to adopt this drainage composite extensively. Nowadays we have the international standard ISO which is coming up, it's in draft stage. ISO 18228 part 4. Apart from that, Indian standards are available. With this, thank you very much for patiently listening.
Thank you very much, Dr. Thankar, for in-time presentation. I request our chair to present the memento to Dr. Thankar.
Thank you, sirs. And we have the last keynote lecture in this session now. Request the chair and co-chair to take over.
So the last talk coming up in this session is keynote lecture 15 by Professor N.K. Samadia, past President Indian Geotechnical Society and Professor Indian Institute of Technology, Roorkee. And he'll be delivering a talk on rock mass characterization and evaluation of support for Alpa Chakri headrest tunnel. I welcome you, sir.
Okay, thank you.
30 minutes.
Thank you so much. I would like to thank the organizers for giving me the opportunity for the lecture, which the topic is the rock mass characterization and evaluation of supports for North Chakri headrest tunnel. Now, before I start, in geotechnical engineering, there are 2-3 quotes you can say are saying that, and that is very important, especially for geotechnical engineers, like judgment comes from good experience and experience comes from bad judgment. And we learn through failures. Now coming to the rock mass. Now there is a saying again that strength and weaknesses go together. Now you will have different strength of rock, intact rock, but when you include the discontinuities, then the strength becomes less. And finally, another saying is that everybody has got an ego. So here ego is redefined. That is extraordinary geological occurrences. So we have got the ego of Himalaya also. So if we want to construct any project in Himalaya, we will have to satisfy the ego of Himalaya. Okay. So in majority of the mega hydroelectric projects in India, there are different components of the hydro projects, and one of them is the headrest tunnel. Now as far as the hydro potential of India is concerned, we see that there are vast river systems which offer enormous hydropower potential, and we can economically exploit it. Approximately 135,000 megawatt is available as per CEA 2023, and Himalayan river systems are especially suitable for hydroelectric projects. Now, in northern region it is about 88,000 megawatt, and in Arunachal Pradesh itself it is 50,000 megawatt approximate potential. Now, in these, all the hydroelectric projects, there are engineering challenges. Now, here I have written it as issues like extraordinary geological occurrences, especially for the determination of the support pressure, or in the case of the support design. And this tunnel construction encounters especially the high in-situ stresses if the structure is situated in the areas very near to the MCT, or maybe the shear zone containing shear zones. Now here I am taking up a study which we have conducted for the Nathpa Chakri project, which is situated in Himachal Pradesh. Now this Nathpa Chakri project is in Satluj Basin, and it represents engineering milestone, notably because its headrest tunnel stretches to about 27.4 kilometers and having a diameter of 10.15 meters. So we can say here in Himalayan region, this is the longest power tunnel constructed in the complex geology. Now it traverses rugged terrain, coping with rock covers of substantial thickness, managing heavy groundwater inflows, and overcoming ground behaviors such as squeezing, slabbing, and there are presence of shear zones. So this is the layout plan of the Nath Pachakri project. Here you can see that on this side it is the Nathpa edit. So the dam is in Nathpa and the powerhouse complex is in Jhakri. So there are different geology traversing all through this Nath Pachakri headrest tunnel. Now you can see this is a drop of about from 1490.5 meter FRL up to 975 meter at the powerhouse area. Now this is the geological plan of the project area. You can find that different formations you can see here. Jero, Wangdu, Naisip complex, and maybe Manikarn formation. There are a number of rock masses which are available with different shear zones, joints, etc., and different type of rock formations. This is the geological plan along the tunnel alignment. Now you will find that from debris up to different type of gneisses, and then you have got different faults also. Now, I will not be going in the details of every zone, but you can see majority of the rocks, these are the medium to coarse grained gneiss, gneiss, quartz mica schist, and those you will find that there are anticlines, there are synclines, there are shear zones, and because of that there is the possibility of the squeezing ground condition also in different regions of the tunnel. So this is the geological section along the tunnel alignment. You can see from the Nath Edit up to the, let's say, Mangalad left bank edit. You will find all the joints are inclined in almost all the arbitrary directions, and also we have got different thickness of the shear zones, so it makes the construction and also design complex. Now, in case of the determination of support system, what we do, we actually start with the rock mass classification systems, and there are a number of rock mass classification systems which are available, and I agree with the previous speaker that one size doesn't fit at all for all the cases. So similarly here, one rock mass classification system doesn't fit for all the cases. You will find that these are the prevailing rock mass classification system starting from Tarjagi theory 1946, and nowadays we are also using geological strength index. So all these rock mass classification systems have got the limitations of one or the other type, because all the classification systems have been developed for different geology, different rock mass conditions. So we cannot use the rock mass classification system as it was developed for some of the geology or the rock mass conditions to the Himalayan geology directly. Especially the mostly we use either the RMR or the Q system, but in Q system also the Q system omits the stress reduction factor values for the competent rock, especially in the moderately jointed rocks categories L, M, N in the table. So there are different theoretical gaps. Here in India also there are semi-empirical methods which have been developed by Roorkee group, and we are using that for determination of the support pressure. So key recommendation is there is urgent need for region-specific modifications to the rock mass classification systems, and also validation of the new theories. Now, in this particular study, we have used basically the rock structure rating system, RMR system, Q system, and RMI, and also for the debris, somewhere SPT values or rock core recovery are available, that data has been used. So, the total tunnel sections which have been analyzed in this particular case are 685 tunnel sections. So we have done the rock mass classification and we have evaluated almost all the classification systems. The total length is about 22 kilometers. Now out of these cross sections, there are 50 sections in the squeezing down conditions, covering a length of about 1.13 kilometer, and you can say length, it stretches from 3 meter up to 63 meter. There are shear zones encountered, so total zones are 69, and also deep cover zone, especially challenges between 10,900 meter to 12,700 meter, 800 meter tunnel length varying. The rock cover is of the order of 1 kilometer or so. So it required special design considerations due to the stress-induced failures. So this is the overview of the tunnel alignment from challenge 10,900 to 12,700 meter, and the maximum rock cover is of the order of 1,430 meter at challenges 11,435 meter. So because of this, it lies in a zone of high overburden, which makes stress-induced failure and deformation significant, and these are all of engineering concern. As I said, rock type encountered are the massive gneiss, schistose gneiss, and quartz mica gneiss, and there are intrusions of amphibolite, pegmatite, and quartz veins, and this rock mass is very heterogeneous, and it contributes to localized stress concentration and spalling, and also in some part the rock burst. The foliation planes, these are spaced at 75 to 300 millimeter, and in some of the cases these are striking parallel to the tunnel axis, which is the worst condition you can see. We try to avoid the tunnel alignment in the direction of the you can say strike of the joint. Steeply dipping transverse joints are also there, and major shear zones have also been identified. So what we have done, we have first studied the rock structures which are available. So this is one of the tables. There are n number of tables in the, because we have studied about more than 650 tunnel sections. So here there is different degree of faulting and folding, and because of that there are presence of shear zones, and there are the squeezing or non-squeezing ground conditions developed. So this is one such table which is giving you some idea about the complexity of the geological strata. So rock engineering properties were determined because in every rock mass classification system you need the rock engineering properties. So these properties were determined through the in situ and laboratory testing. The in situ testing was done by Central Soils and Materials Station CSMRS, and multiple rock mass classification systems were applied, and since the data was used, so interactive computer program ROMA-C, it was written in C++ for the classification systems to be used. So here RSR, RMR, RMI systems are used. Now again, this is one of the tables. You will find that in order to find out the or maybe Q or any other classification system, parameters are required, and the parameters are type, and we need index properties including dry unit weight, saturated unit weight, unit weight of soil, the specific gravity of the rock, porosity. So these are the index properties which were determined at the CSMRS lab. Then they have also conducted the unconfined compressive strength test and also the triaxial strength and tensile strength which are required for different classification systems. So in different areas like from North Fast Holding, Batal and Maglad, these are some of the properties which are given, and on the basis of these properties have been used to include in the rock mass classification systems. Now, this is another table which shows so again there are again a number of tables here. It is from challenge 0 to 680 per meter. So what is required? What is the overburden? If there are shear zones, what are their orientation? What is the thickness? What is the depth, strike? Geological structure, whether it is faulted or folded, what type of rock it is available, what is the unconfined compressive strength, and what is the RQD. Based on the core recovery, they have determined the RQD, how many number of joint sets are there, and then what are the joint properties. There, the driving is in the direction of the strike or dip, what is the specific spacing of whether they are continuous joint or not, then what is the roughness, is there any weathering, alteration, what is the groundwater condition, and finally, in order to find out the Q, what is the SRF value. So all this data has been collected, and finally Roma C was used to finally classify the rock mass. Now, as I said, different rock mass classification systems have been used, starting from RSR to RCR, and for different categories. So these are in this particular table, the minimum and maximum values are reported here. Let us say for RSR, it is minimum 25 and maximum it is at 76, and corresponding to that, the challenges are also given. And also the ground conditions, in non-squeezing ground condition and squeezing ground condition, what were the values, those are given here, and especially on the basis of Q value, you can see here the value of Q is ranging from 0.001 and it goes up to, in the non-squeezing it goes up to 8.08. So, because sometimes what we do, we use different classification systems, but if some value on the basis of one classification system is available, then we try to convert it into other classification system values. So there are like different correlations available between Q and RMR. So here what has been done, an exercise has been done to correlate different classification systems like between RMR and RMI, RMR and rock mass number. In this rock mass number, only difference with the Q is that in rock mass number, we use SRF equal to 1 and remaining parameters remain same. So again, n number of plots you will find. Then on the basis of this different classifications, the interrelationship between different classification systems have been obtained. And on the basis of this, especially for the Himalayan rocks or Himalayan geology, we can use these interrelationships for the classification systems with a certain degree of confidence, because we cannot use the classification system which we have developed for different rock mass, we cannot directly use for the Himalayan geology. So some of the correlations which are given here, and also the what we can use with 90% confidence limits. So like you can see here that at number 5, RMR equal to 4.7 log natural log Q plus 56.8, and this such type of classification system which are available in some textbooks also. So here we have proposed that we can use these rock mass classification correlations if you have information on some other system, you can convert it into the different system and you can use it to determine the support presses. Now, even today, in order to design the support system, we make use of these log mass classification systems, and then finally deciding about the support pressures or the support requirement, we try to corroborate it with the advanced methods like we can use finite element method or some other numerical method, and we try to find out that whatever we are getting from these numerical method, it was whatever we have got from the classification system, is there any correlation? If not, then we can improve the support design support system. So we have evaluated the support presses, and as you know that designing tunnel support is a highly complex task, chiefly because of the geological environment is unpredictable. Because again, here comes the extraordinary geological occurrences. Whatever investigation program you use, there may be some surprises also available, which remains, you can say, uninvestigated, and we get the geological surprises. So modern engineers often depend on empirical classification systems like Q system to guide their choices of tunnel support conditions. Within the Q system, there is a term which we call it as the stress reduction factor. It is recognized as a crucial yet frequently debated parameter. Or we can say it is a contentious parameter. It is very difficult to find out the value of SRF, as it exerts a major influence on the calculated value, and if suppose that parameter is wrong, then the whatever new value you are getting, that will be wrong, erroneous, and then the support pressure which you will find out, that will also be erroneous. So when SRF is selected incorrectly, especially in the case of moderately jointed rocks, there can be significant errors leading to unreliable support designs and potentially unsafe tunnel structures. So here, classification values and roof support pressures which have been obtained, there are correlations available between the roof support pressure and also the RMR classification system. So based on the values available at different challenges, RSR, RMR, RCR, QN and RMI, the support pressures have also been calculated, and these values are given in megapascal. Like for the value of 0.442 in challenge 0 to 50, on the basis of Q, the support pressure comes out to be 0.177 megapascal. So standard empirical correlations are available for the support pressure. We can find out the roof support pressure, and then based on the value of QW for the wall support pressure, correlations are given by Bolton et al, and those can be used. So in some of the cases, it can be the squeezing ground condition, it can be the non-squeezing ground condition also. So we have evaluated which support pressure system should be used, or which will be conservative and which is giving you the less value of support pressure which is actually required. So on the basis of different support system like rock structural rating, RMR, rock mass rating, Q system, N system and RCR system, these are some of the values which we have got. Like based on Q system, the pressure is ranging from 0.01 to 1 megapascal. In 94% of the sections in non-squeezing ground condition, it is less than 0.34 megapascal, whereas 65% are between 0.06 to 0.18 megapascal and maximum at 0.1 to 0.14 megapascal. So similarly, for all other systems also, we have here I have presented on the basis of the values which we have got, and this is presented in this particular plot where the number of sections is percentage versus the pressure range. Which particular classification system lies in which particular pressure range. So percent tunnel sections in different pressure ranges for all classification systems in non-squeezing ground conditions. Now similar to this, we have also determined the support pressure in the case of the squeezing ground condition, and in the squeezing ground condition you will find that so comparison are also given here, like RCR shows highest, others are minor. RCR actually underestimates the support pressure in case of squeezing ground condition. So for squeezing ground condition classifications which are assessed are RMR, Q, N and RCR. Because RSR system is not applicable for squeezing ground condition, and for the RMR, normally we use this RMR for the slopes etc., but in some of the cases we also convert this Q into RMR, and then RMR is used to determine the support pressure. So basically we go for Q system, and in this Q system, in the case of the squeezing ground condition, you will find that we have found that the 44% sections are in this category in which we are getting the support pressure of the order of 0.2 to 0.4 megapascal. So we have compared the different classification systems, and then so this is the now squeezing can be mild, squeezing can be moderate, squeezing can be high. So these are the support pressure ranges and the number of tunnel sections in which we have got for the case of the mild, then it is for the moderate squeezing, and this is for the high squeezing grounds on the basis of RMR, Q, RCR. And what project authorities, they have provided the actual support. So the project authorities have also, on the basis of these classification systems, they have provided the support system. So these are the comparative insights. Consistently gives the low pressure estimates. I will have to move a little faster, and the 3 minutes are available. So this is the comparison here, that the P on the basis of RMR is less than RCR, less than Q, and that is less than mass number. Now, the crux of the analysis is that the SRF value which we use for the moderately jointed rock, it does not give the actual value of the Q, which can be used for the estimation of support pressure in case of Himalayas. So what we have done, we have assumed this SRF value equal to 1, that is nothing but N, which is developed by Goel et al. For Himalayan rock conditions. And then we have compared, especially for the moderately jointed rock, the category L, M, N, and we have suggested that the values of the SRF which are proposed by Martin et al., those should be reduced to this particular level so that these can be used for the Himalayan conditions. So here, the SRF problem. In the Nath Pachakri tunnel, rocks were moderately jointed, incorrect SRF application suspected, overestimation of support pressure observed. So we have used the classification system given by Goel et al., RMS rock mass number N with SRF value equal to 1, and we compared the estimated roof support pressures for these categories, and the goal was to adjust the SRF input system for moderately jointed rocks. So in order to compare that, again we have developed relationships, and then we have compared the roof support pressure obtained from Q and roof support pressure obtained for N for different values of SRF. The Q system has given that for the moderately joint in the case of category L, the SRF should be equal to 9. So we have done the analysis for different SRF values, and finally So this is for 15 for category M, and this is for SRF equal to 20 for category N. So we have done the analysis, and finally we have obtained that using the condition in which P obtained from rock mass number and P obtained from Q, so Pn less than Q, Pn equal to Q, and Pn greater than Q, we have obtained the maximum deviation, we have got the standard deviation, and we have got the correlation coefficient for category L, M, and N. And finally, we have recommended that for the category L, M, and N, sorry, last one is L, N. So the original values which are given by the Q system, these should be reduced to, so like in place, it should be 1.5 to 2 for moderately jointed rod, 2 to 2.5 for moderately jointed rod in this category M, and finally 2.5 to 3 in S, against 15 to 20 in the case of N. So, conclusions, I have tried to finish in time, so I have to rush. So, comprehensive geotechnical data was compiled for over 685 tunnel sections, covering 22.2 kilometers of the tunnel, enabling robust analysis and validation of autonomous classification systems. A computer program C++ was developed just to add. Then correlation between different classification systems have been developed. These correlations may be applied for Himalayan geology. We have estimated the support pressure, and we have given the correlation for SRF also. And in non-exclusion ground condition and in exclusion ground condition, we have compared the support pressures, and the support pressure support system recommendations have also been given, and the comparison is given for different classification system. And finally, the Barton's Q system does not adequately suggest SRF values, that is the stress reduction factor for LM and category. Through the present study, new SRF values have been proposed for these categories, improving the applicability of Q system to the local geology. And I am happy to say that the Bureau of Indian Standard has also adopted these particular SRF values for L, M, N category. So thank you so much. These are some of the references. And I would also like to thank Dr. Naresh Kumar. He is Chief Engineer, Central Water Commission, retired. And he has collected the data because he was in Central Water Commission, so he had access to all the data which was available for the Nagpa Jhakri project. Thank you so much. This is our Civil Engineering Department, so I request all of you to visit IIT Roorkee, Department of Civil Engineering. We keep on organizing many activities under the aegis of Indian Geotechnical Society. So finally, again, I would like to thank Dr. Ashish Juneja, Dr. Dasaka for giving me this opportunity. They know how important this particular lecture is for me. Thank you so much.
Thank you very much. Also, we have 4 excellent lectures by Jaido Digby on nature and geogrids, and she has also presented some case studies showing how we can have a lot of savings by using these techniques. Then there was a nice presentation, Dr. Harikrishna breaking the myths about ground improvement and bringing out the reality. Dr. Nagar Mahajan presenting green initiatives using geosynthetics. And finally, Professor Samadhyas was presenting extensive study on geological studies of rock masses in headrest tunnel of Nagpa Jhakri project. So big round of applause to all 4 speakers today. And big round of applause to delegates also, because it is day 4 and that too in Goa, and we are having a quite large number of delegates attending the day 4 session also. As regards the nature and geosynthetics, I would like to tell that you must have seen on the roads while coming from airport to or from railway station to this venue. The roads are lined by coconut trees. The earthworms are supported by coconut trees on the edges, and these are acting like tree roots, which are acting like geosynthetics, and these are supporting the environment for a very long time. Not only for roads, also for water bodies, earthenworms retaining water bodies. The tree roots which are spreading, these are fibrous in nature and quite thick, these coconut plant roots, and they are going for almost 2.5 to 3 meters, and they have supported embankment for several years. Thank you very much.
Thank
Now I
you,
hand
sir.
over to the organizers.
To hand over a memento to Professor K. Samadhya, I request the chair and co-chair to kindly come forward. Thank you, sir. And now to present a memento to the chair and the co-chair of plenary session 9, I invite Professor S.K. Prasad, member of the International Networking Committee of Geotech Asia 2025. I request the chair and co-chair to kindly accept a memento on behalf of the organizing committee of Geotech Asia 2025. Request Professor K. Samadhya to, request Professor S.K. Prasad to hand over the memento to the chair and co-chair. Thank you all. Now we have tea coffee arranged outside. We will start the plenary session 10 at 11 a.m. In the plenary session 10, we have a special invited lecture, a special guest lecture, and yet another invited lecture. So request all the delegates to be back in the hall by 11 a.m. so that we can start off with the plenary session 10 on time. And the presenters for the next few sessions of the day, whoever hasn't handed over your presentations at the console, request to hand it over during this break as well as during the lunch break if you have a presentation post lunch.